Hello students, today we are taking up the extended version of moment of inertia topic, and we will see when we talk of moment of inertia, two things are very important for us to understand. When we talk of moment of inertia, first one is the rotational motion and the other one is the rigid body, and we had seen a very simple formula coming up for the moment of inertia as moment of inertia equals to mass of the body and square of the distance from the axis of rotation. Okay, now suppose when we talk of moment of inertia, we talk of two theorem of parallel axis and theorem of perpendicular axis. Okay, now when we talk of theorem of parallel axis, so this is a rigid body, this is the rigid body. We have got one axis xy passing through the center of mass, and this is given as I suffix c, and we have got another axis that is x dash y dash. Now the moment of inertia along this particular axis x dash y dash is equals to, this is what we are talking about, I. So this equals to moment of inertia passing through the center of mass plus the total mass of the body and the square of the distance between the two parallel axes. So here we have got I as the moment of inertia about x dash y dash, and I suffix c is the moment of inertia passing through the center of mass plus the total mass of the body and square of the distance between the two parallel axes. When we will be doing the applications, we are going to use it. The next one is theorem of perpendicular axis. Now what exactly, suppose if we have got I suffix x as the moment of inertia, my is the moment of inertia along x axis. Okay, we have I suffix y as moment of inertia along y axis, and I suffix z is the moment of inertia along z axis. Okay, so this theorem states that Ix is equals to Iy plus Iz, or we can write Iy is equals to Ix plus Iz. Most of the time the students make some mistakes. One theorem, one line is given. When they need to find out Iy, they simply do algebraic computation on this. They will write Iy is equals to Ix minus Iz. So but Iy is equals to Ix plus Iz, and we have got Iz is equals to Ix plus Iy. So this we need to understand what we are talking about, the moment of inertia, right? Where x, y and z axis are mutually perpendicular axis. Okay, so let us, if we have to prove this, very simple proof is there. Suppose if we have taken this as the body, let us assume we have taken three different axes, they are mutually perpendicular to each other. This is O. Let us assume this is x, we have taken this, we have taken y, and this side we have taken z, right? Now we consider a point P, and this point P is at a distance r from the which axis? From the z axis, and this is at a distance y from x axis, and this is at a distance x from y axis, right? So it simply shows that the moment of inertia along the z axis, and if you look into the corner of the room and then you try to find out, you will come up with one formula: r square is equals to x square plus y square. It is simple Pythagoras that we are using it. Now the moment of inertia along z axis is I equals to Iz equals to sigma mr square, and we can write this as equals to sigma m x square plus y square, right? So let us write Iz is equals to sigma mx square plus sigma my square. We can just segregate the top and we can write, but this is the moment of inertia along the y axis. So Iz is equals to Iy, and this is Ix. Okay, so what we have got, the moment of inertia along the z axis as the sum of the moment of inertia along the other two axes. Iz equals to Iy plus Ix, so we are getting up these conditions. Okay, so this is what we had, the theorem of perpendicular axis. But then again, earlier I told you we are bothered about the application parts. We want to see for the applications. Let us take a simple condition where we have taken a rod. This is the rod we have taken, and this is the axis which is passing through its center, and it is perpendicular. Suppose if I take this rod, then this axis is passing through its center of mass and it is perpendicular to it. Now in this case, when we have taken this condition, then the moment of inertia I c suffix m is equals to m L square by 12. This is the moment of inertia passing along the axis xy, ml square by 12. There is a derivation, complete derivation based on this part, but let's not go for the complete derivation. Now, suppose if I take another axis which is passing through its end, let us assume this is x dash and y dash. We need to find out the moment of inertia along, and the total length is L of the rod, and the total mass is given as capital M. Now suppose if I have got an axis x dash y dash, and I am interested in finding out the moment of inertia along this axis x dash and y dash. So how I can find? I have only one thing with me, that is the center of mass moment of inertia is ml square by 12, but I want to find out for this axis. If I get to see the figure, then these two axes are parallel to each other. So obviously we are going to use the theorem of parallel axis. What does it state? Moment of inertia along x dash y dash is equals to a moment of inertia passing through the center of mass, which I have already written here, plus the total mass of the rod, let us assume it is capital M, and the square of the distance between the two parallel axes. So what is the distance between these two parallel? It will be L by 2. It's very understood. From here to here it is L, so from here to here it is L by 2 because it is passing through the center of mass. So applying the theorem of parallel axis, we get I. I is the moment of inertia along x dash y dash is equals to ICM plus M and distance square. We are using this formula. So this is ml square by 12, right? Plus what you are getting? M, and this is L by 2 ka whole square. So this is ml square by 12, ml square by 12 plus ml square by 4. So if you compute, you are getting up this as equals to ml square by 3. Right, so we have got this. So what exactly is needed? What is needed? You need to understand, need to assume, you need to think of. If you cannot assume, if you cannot imagine, you cannot consider a case where we are finding out. Next class we will see more of the figures, and we are going to apply these two theorems, that is the theorem of parallel axis and theorem of perpendicular axis, to solve more and more. Thanks for watching.